Good morning, everybody. Welcome back to Calc 2. Plan for today is we're going to continue our discussion of improper integrals. Focusing today on looking at a special type of integral called a p-integral. And then seeing what happens if we try and get kooky and introduce some imaginary numbers into the mix. As far as office hours go, I've got my usual office hours for the next few days. 11 to 12 and 1 to 2. No new homework assignments. Set it on the first exam date. It's going to be next Wednesday. So Dr. Gerstel, how do exams work on the mastery-based grading system? So what's going to happen is next Wednesday you're going to come in, I'm going to hand you the exam, and it's basically just going to be a bunch of quizzes stapled together, essentially. So there'll be like one page that has like standard 1 stuff on it, one page for standard 2, one page for standard 3. Up through, let's see, by next Wednesday, hopefully standard 7. Your job when taking the exam is to get as many masteries as you can within the 65-minute time period. You don't have to you can skip over and just not do any questions or any standards that you already have 2 masteries in. This is just kind of your opportunity to show me what you've got on every standard that we've covered so far. And yes, you'll know going into the exam how many masteries you have in every standard, so you know how many you still need to test over. Maybe you need masteries in all 7 standards still. Maybe you only need masteries in like a couple of them going into Wednesday, but you'll be able to test over the ones that you need to. But essentially, think like a bunch of retests all at once. Any questions or comments about the exam? Here's one thing I'll let you have for the exam. You are allowed to bring in 1 sheet of notes, front and back, whatever you want written on it, into the exam. So if you want to kind of bring in a sheet that has all the inverse trig derivatives and integrals and such, go for it. If you want to have some sample problems worked out on that sheet, go for it. That's the reason why I let you put together a note sheet is I think putting together a note sheet, deciding what would be helpful for you is actually a great practice or a great study tool for the exam. So keep that in mind. Yes?
Is it like a full sheet of paper or just a note card?
A full sheet of paper. So like one of these, front and back. Except this one's 2 pages stapled together. Don't do that. Yep. Full sheet, front and back, and every other exam you'll also be given that as well. Any other questions or comments about the exam? Did you all know having 1 wife is monogamy? Having 2 wives is bigamy. But having 3 wives, that's trigonometry. Okay, so last time we introduced the idea of what it means to take an improper integral. Where improper integral, the idea is we're integrating over some unbounded region. So in this case, for a type 1 improper integral, typically we're integrating from some fixed constant like a going all the way out to infinity. And basically saying, hey, we sort of have this shape with an infinite perimeter since it extends out infinitely far this way, but can it still be the case that the area comes out to some finite number? And we said that if the area comes out to some finite number, then we say that the integral converges. And if the area doesn't go to some finite number, then we say it's a divergent integral. And the idea behind how do you integrate a function from, say, a constant like a to infinity, well, you just integrate from a to a variable r to get an expression in terms of r, and then you take a limit as r goes to infinity. So last time, we looked at a couple different integrals. We looked at integral of 1 over x cubed And we also checked out an integral of something like 1 over x. And these gave us sort of integrals over similarly looking regions. This one had an integral that was something like this. And we said that that came out to a finite value of just plain old vanilla 1/2. Whereas this integral, integrating from negative infinity to -2, see that this one diverged. Because when we took a limit as r goes to negative infinity for that one, we got that the area went to negative infinity. Whereas in this case it went to 1/2. So that even though these were two similar sort of looking regions, I'm at least trying to eyeball my beautiful hand drawn graphs, that somehow the integrals behave very differently from each other. So what I would like to do today is I want to start off by looking at integrals that look of functions that look like these, 1 over x versus say 1 over x cubed. And what we're going to do is we are going to define what's called a p-integral to be the integral to be a type 1 improper integral of 1 over x. So if you're following along in the packet, I'm going to be on page 3. So in general, we're going to define a p-integral to be an integral of the form from 1 to infinity of 1 over x to the power of p. So for instance, this would be a p-integral right here for p equal to 3. Because we have 1 over x to the power of 3. And the question I want to look at today is for which values of p does this integral converge? And then for which values of p does this integral diverge? Y'all ready? A few half-hearted nods, I'll take it. Alright, here we go. So we're going to take integral from 1 to infinity of 1 over x to the p power, where p is some constant. We don't know what p is equal to specifically, but we know that it's going to be some constant. So our final answer is probably going to be some expression in terms of p. So first step, so as always with a type 1 improper integral, we're going to take a limit as r goes to infinity, integral from 1 to r of 1 over x to the p. And then I'm going to rewrite 1 over x to the p as x to the power of negative p. So let's take a look at this integral right here. How would we evaluate the integral of x to the negative p, where p is just some constant? Bethany, how would you approach that integral?
Well, since we know how to differentiate or integrate it using the reverse of the power rule, then we can just do like negative p plus 1 divided by, or negative p plus 1, like x to the negative p plus 1 all over negative p plus 1.
Yeah, this is just a power function. X to the power of a constant, something that we can use the reverse power rule on. So this expression is going to be equal to x to the negative p plus 1 all over negative p plus 1, evaluated from, say, 1 to r. Bethany, can we do that? Can we do that? Is that what it's always going to be, no matter what value of p you plug in there? Or are there some values of p where you would have to integrate this somehow a little bit differently? Phoebe?
Can't you not use the reverse power rule and equals 1?
Yeah, if p is equal to 1, what goes wrong here?
You would be dividing by 0, I think.
Yeah, well, we'd have a big problem here if p is equal to 1, because then you'd be taking x to the 0 all over 0, which would be no bueno. Are there any other values of p that this doesn't work for? James? So you have your hand up.
I don't think so.
I don't think so either. So this works in every case except for the case where p is equal to 1. What does this integral come out to if p is equal to 1? How would we integrate x to the negative 1 power? Well, if x to the negative 1 is just 1 over x, Reagan, how do we integrate 1 over x?
It'd be ln of absolute value of x.
Yeah, it's just going to come out to absolute value of natural log of x, evaluated from 1 to r. So we basically have two separate cases we need to consider. Bless you. The case where p is equal to 1, in which case we just have the natural log to worry about, and the case where p is something other than 1. So let's talk through each of those separately. Mary, which one would you like to start with? The p equals 1 or the p not equal to 1 case? P not equal to 1. Cool. People miss these days. Try to stay off the side more. So let's look at the case where p is not equal to 1 then first. So if p is not equal to 1, we get the limit as r goes to infinity of x to the power of negative p plus 1 all over negative p plus 1, evaluated from 1 to r, which is what? Same as limit as r goes to infinity of r to the power of negative p plus 1 all over negative p plus 1 minus 1 to the power of negative p plus 1 all over negative p plus 1. And here that's just for plugging in x equals r and x equals 1 here. Carson, what's this going to simplify to? Of course. Nolan, what's 1 to the negative p plus 1 going to simplify to?
1.
Yeah, doesn't matter what p is, 1 to any power is always just going to give you back 1. So this term will simplify down to just 1 over negative p, or minus 1 over negative p plus 1. Let's look at this expression. Here, we can pull, since p is a constant, we can pull 1 over negative p plus 1 out in front of the limit as a constant multiple, and take 1 over negative p plus 1 times the limit as r goes to infinity of r to the negative p plus 1. reason why we can pull the negative p plus 1 out in front of the limit is it's a limit as r goes to infinity. 1 over negative p plus 1 is just a constant multiple here. So what is this limit going to evaluate to? So this one's tricky, because we're going to get two different answers depending on what r is equal, what p is equal to. So let's look in the case where r is equal to 999, for instance, just a big number, so we can get some intuitive sense of what we think this integral is going to come out to be. Kate, if I were to take 999, a big value of r, and then raise that to a power like, I don't know, 3, is this number going to come out to be something really big or really small?
Big.
Yeah, I would say it's pretty big. Ty, how about if I took something like 999 and then took it to a negative power, like negative 3?
Something small.
Yeah, that's going to be the same as 1 over a really big number, which is going to be something small. So the idea is, if we're taking a really big number and then taking that to a positive power, that limit is going to go to infinity. So specifically, this limit right here is going to go to infinity in the case that our exponent, negative p plus 1, is greater than 0. Which is the same as saying if p is less than 1. Because if you add p to both sides of this inequality, negative p plus 1 being greater than 0 is the same as saying p has to be less than 1. What do we get if our exponent is negative? So if we take a really big number like r, and then we take that to the negative power and let r go to infinity, what would we expect this limit to be equal to? James?
Negative infinity?
Negative infinity? Is that the sort of thing we get if we take
Oh wait, no.
a big positive number to a negative power like negative 3?
No, then it's 0.
Now it's 0?
Yeah.
Bethany, what do you think?
Yeah, 0.
You agree with 0? Yeah. Turns out this comes out to 0 in the case where negative p plus 1 is less than 0. Which is the same as saying if p is greater than 1. Because if we add p to both sides of this inequality, then we just get 1 is less than p, or equivalently p greater than 1. So that tells us something. It's going to tell us that this integral up here is going to diverge in the case where p is less than 1. It's going to converge in the case where p is greater than 1. Any questions or comments about how we set this up or evaluated this? The idea here is having a really big number like r, if we're taking a really big number to a positive exponent, so if this negative p plus 1 is positive, that's going to go to some really big number. In fact, the limit's going to go to infinity. But if we take a big number r and take it to a negative exponent power, as r gets bigger and bigger, this sort of expression is going to go closer and closer to 0. Alrighty, Neato Dorito. So with that, we still need to consider the p equal to 1 case. So let's take a look at that one. We're not going to plug p equals 1 in here because this was because we only this case only held in the p not equal to 1 case. If p is equal to 1, then our expression over there integrated to something completely different. So let's do the p equals 1 case separately. So in the p equals 1 case, we're going to get a limit as r goes to infinity of what? Natural log of absolute value of x, evaluated from 1 to r, which is the same as the limit as r goes to infinity, natural log of absolute value of r, well, r is positive here, so we're going to say natural log of r, minus the natural log of 1. Natural log of 1 is just 0, so we don't have to worry about that one. As r goes to infinity, what's natural log of r going to do? So if here's a graph of the natural log function, it looks something like this. Rhoda, what's as r goes to infinity, what's natural log of r going to do?
Also go to infinity.
Yeah, this is going to go to infinity. So it's going to diverge in the p equals 1 case. It's going to diverge in the p less than 1 case, but it's going to converge in the p greater than 1 case. And in fact, we can kind of sum up what we found by seeing that the overall integral of 1 over x to the p from x equals 1 to x equals infinity, we're going to say that this integral diverges if p is any value less than or equal to 1. If p is less than 1, then we have this expression and we get a limit that goes to infinity. If p is equal to 1, then we have a different limit, sort of limit appearing, but it's still a limit that goes to infinity. This integral is going to converge if p is greater than 1. And what value is this integral going to converge to? So we're in the case where p is greater than 1. What does this expression evaluate to in the case where p is greater than 1? So we're in the case where p is greater than 1, so this limit right here comes out to 0. So what would this whole expression come out to if this piece right here was 0?
Infinity.
No, I don't think infinity. We're going to get stuff times 0, and then minus 1 over negative p plus 1.
Negative 1 over negative p plus 1.
Yeah. This is kind of the only part that's left. It's going to converge to the value of negative 1 over negative p plus 1. Or if you want to do it without as many negative signs, you could rewrite this as 1 over p minus 1, which is a more common way to probably write that out. Which you can get that from just multiplying numerator and denominator by negative 1. Well, I think that matches up with what we talked about last time, where we said last time, if we took an integral from 1 to infinity of 1 over x cubed, we got a half, which is the same as 1 over 3 minus 1. If we wanted to take an integral from, say, 1 to infinity of 1 over x to the power of 1.01, well, that's going to give us 1 over 1.01 minus 1, which is 1 over 0.01, which is 1 over 100th, which is 100. And we can even say, for instance, the integral from 1 to infinity of 1 over x to the power of 0.99 diverges. That integral is going to go off to infinity, in fact. So to me, that's kind of really weird that we could have two functions that look really, really similar. 1 over x to the power of 0.99 versus 1 over x to the power of 1.01. Those are functions that are pretty close to each other. The exponent is just like, what, 0.02 off. Yet this integral actually comes out to some finite number, 100 specifically, but this integral goes to infinity. This integral is going to give us a finite area. This integral will give us an infinite one, even though the functions themselves look pretty close to each other. Yeah, Phoebe?
Is the reason you don't have like a negative in the denominator because you just canceled it out with the negative out front?
Like down here?
Yeah, like when you did the examples.
Yeah, so the reason why we don't have a negative in the denominator is when we define a p integral, the p is already assuming that x to the p is in the denominator. I mean, if you want, you could write this as, it's the same thing as integral from 1 to infinity of x to the power of negative p. And then if we tried to plug in, say, 3 into this expression, we'd have x to the negative 3 power, but it would still come out to the same answer in the end. Why do we call that a p integral and not like a negative p integral? I didn't come up with it. I think mathematicians just wanted to consider the case mainly where x to the p is in the denominator. Because if you were to take something like integral from 1 to infinity of, I don't know, x squared, where the function keeps getting bigger and bigger the further you go out to the right, what would you expect that area to come out to? Yeah, it'd be infinity. It'd be super infinite, if such a thing existed. Take real analysis to learn more. Because not only as you go out further to the right, you're adding on more and more and more area. The area is just growing at a super big rate. Whereas take something like 1 over x to the 0.99, which has a graph that looks something a lot like this, where you have positive area, but it keeps shrinking. The further and further you go out to the right, the less and less area you're going to be adding on. And I would say, with an area like this, it's super obvious that the area is going to infinity. In this case, just looking at the graph, it's not so obvious. Is this area going to be positive or negative? Or, well, not positive or negative. Infinite or finite. So, typically, these are the integrals that are more interesting to us to try and look at. The case where it's not so obvious, is this area going to be finite or infinite, compared to if we just said, take integrals of the form x to the p, which if p is greater than 0 is always going to give us a really big infinite area. Any other questions or comments related to this? Alright, so I promised you all some fun with imaginary numbers, and I aim to please. What's the number I? Somebody see seen that before in a previous math class? Kate, where have you seen I before?
Algebra 2.
Algebra 2? Oh, how is it defined in that class?
Isn't it like the square root of -1 or something?
Yeah, we define I to be square root of -1. Which is the same as saying I is a number that when you square it, you get -1. Now, I is called oftentimes an imaginary number. Why would you call a number like that? Why would you call a number like square root of -1 an imaginary number, do you think? James?
Because you can't really graph it on like a real number plane.
Yeah, there is no number on, say, the real number line that when you square it, you get -1. If you take a real number and you square it, you're always going to get something positive, unless you're squaring 0, in which case you get 0. So there is no real number that when you square it will give you -1. And yet, in spite of that fact, we still talk about I as being a number. There's a lot of interesting philosophical debates we can get into here. Like I could say, for instance, Joy, do you believe that the number 3 exists?
In what sense?
In any sense you please.
Yes.
Okay. Let's specify. Does the number 3 have some sort of physical existence?
As an original form or as like a representation?
Good question. Interpret it as you will.
Okay. Then yes.
And yes. It's interesting. Because if I ask you, does number 3 exist? I could say, one could argue, hey, I have 3 pieces of chalk in my hands. There's the number 3, it's right there. Of course, you could also argue, if you're Plato, oh, that's not the actual number 3, you could talk about that as being a physical representation of the number 3, but the actual number 3 has some existence as, say, some sort of ideal form. Or you could be a complete maverick like our computer scientist, Dr. Cipher, and say that the number 3 doesn't exist at all. It's just a useful tool of the human imagination. Whether numbers exist like 3 or 1 or pi is a very philosophical question, because you could interpret that in a number of ways. And I encourage you to talk to your philosophy professors about that. They'll have some interesting ideas. But I could make an argument that if the number 3 exists in the sort of, say, ideal form that Plato espoused, or Aristotle, why couldn't we say the same about I? What makes 3 a more real number than I? Just because it's easier to interpret 3 in a physical sense than I doesn't necessarily make it any more real. That's why calling I an imaginary number, I think I gets a bad rap. I think imaginary here means it's not on the real number line where we take some arbitrary set of numbers and call it real numbers because, I don't know, it's numbers we feel more comfortable with working with. I would argue I can exist every bit as much. Yeah, James?
Don't some people refer to it as a lateral number?
Yeah, there's a lot of different numbers ways you could refer to it, like a lateral number or a complex number. If you're an engineer, you're probably not even calling it I, you're probably calling it J instead. There's a lot of different ways to refer to the same sort of core idea, though. So, here's a question. We know that I squared is going to be -1. What would we expect I cubed to be equal to? Bethany?
Wouldn't it just be I? Or, well,
Not quite.
be a negative I?
Yeah, I think it's going to be -I, because we could write I cubed as being the same thing as I squared times I, which is the same as -1 times I, or -I. How about I to the 4th power? James,
1.
how'd you get 1?
Because it's I squared times I squared, so -1 times -1.
Yeah, a lot of different ways you could think about it. I squared times I squared is probably the easiest, which gives you -1 times -1 is 1. You could also think about it as being like I cubed times I, which is the same as -I times I, which is the same as the negative of I times I, which is -1, which is +1. But I to the 4th comes out to +1. If you think about it, I is sort of like sine and cosine, where if you start with sine and you differentiate it 4 times, you get back to the same trig function you started with. Just like how if you start with I and you multiply I by itself 4 times, you end up back at just 1. And if you take I to the 5th, then you'll get I. Take differential equations if you want to see more connections, or complex analysis between I and the trig functions. So, we know what I cubed is. We know what I to the 4th is. All right, James, answer me this. What's I to the I power?
I don't know.
Bethany, you know that one? I think we have tools at our disposal using improper integrals that we can now use to determine what I to the I is going to be equal to. But to determine that, we're going to have to do some trickery. And it's not going to immediately be obvious how we would go about evaluating that, or what we're about to do relates to taking I to the I power. Because what I want to do is I want to integrate from 1 to infinity 1 over x squared plus 1. And I promise you, at some point, this is going to relate back and tell us what I to the power of I is equal to. Believe it or not, we actually have 2 different ways at our disposal now for evaluating this integral from 1 to infinity of 1 over x squared plus 1. Does anybody, other than Bethany and James, because I've heard enough from them for now, does anybody have any ideas on how can we integrate 1 over x squared plus 1 using some of the previous standards? I'll go ahead and write it to the left like this while you all are thinking about it. Rhoda?
We could do U sub and put x squared plus 1 is U.
Ooh, okay. We could try a u sub. Do u equals x squared plus 1. So then du is equal to 2x dx, which would give us integral of du divided by 2x times 1 over u. Does that seem like it's going to be helpful? Probably not. I don't think u sub is the answer. So what could we do instead if we wanted to integrate 1 over x squared plus 1? Right?
Inverse there's inverse.
Yeah, if you remember, we actually found last standard what function has a derivative of 1 over x squared plus 1. we said that it's just going to be inverse tangent of x. So we can end up just taking a limit as r goes to infinity of inverse tangent of r minus inverse tangent of what? 1. Oh. Actually, okay, I was going to say, why does this not work out? Because I want to do an integral from 0 to infinity. Sorry, not from 1 to infinity. Inverse tangent of 0, that's just going to be 0. So, as r goes to infinity, what's going to be what's inverse tangent of r going to be going to? Might help to have a graph of the inverse tangent function here. And the inverse tangent function looks something like this. Sort of like a tangent function if you took it and you tilted it on its side. You reflected over the line y equals x. So according to this graph, what would we expect the limit as r goes to infinity of the inverse tangent function to look like, Gabe?
Well, does the fact that like the inverse tangent function we only can define them for certain bounds affect this, or?
Actually, inverse tangent function is defined for all real numbers out.
Okay.
Inverse sine and inverse cosine are only defined for x between -1 and 1, because sine and cosine can only have outputs between -1 and 1. But tangent can take on any real number as an output. So inverse tangent can take on any real number as an input.
Yeah, this looks like it would be like that.
Well, according to this graph, I don't think the limit's going to infinity as x goes to infinity. Joanna, if you look at this graph, as x approaches infinity, what does it look like inverse tangent of x is going to? It's not going to infinity. Ty?
Pi over 2.
Yeah, it's going to pi over 2. With the idea being, if we take a look at the original tangent function between, say, negative pi over 2 and positive pi over 2, the tangent function looks something like this. Meaning, as x gets close to pi over 2, y goes to infinity. Well, if we flip around our x and y coordinates, we can say, instead of as x goes to pi over 2, y goes to infinity, we can say it as x goes to infinity, y is going to go to pi over 2 instead. So integral from 0 to infinity of 1 over x squared plus 1 comes out to pi over 2. Neato burrito. What does this have to do with I to the I? Not much. Yet. Turns out we have another sneaky way of evaluating this integral. And this way of evaluating the integral isn't going to depend on inverse trig functions. What other integration technique do you think we could try to use for this? If it's not u sub, and it's not using an inverse trig function, what other ways have we talked about to integrate a function? Katie, any ideas?
Partial fraction decomposition?
Partial fraction decomposition, holy moly. So that would be saying like 1 over x squared plus 1, we would have to factor the denominator, and then we could use partial fractions on it. Can we factor x squared plus 1?
No.
Yeah. If this is a standard 4 question, we would say, x squared plus 1, we can't factor that. Or can we? Ty?
We use I, so like, instead of doing difference of squares, well, do difference of squares, but use I.
The fact that x squared plus 1 is the same as x squared plus, or x squared minus I squared? Yeah! If you allow imaginary numbers, we can write this as 1 over x plus I times x minus I. Oh me, oh my. And then we could try and solve for constants, a and b, that'll make a over x plus I plus b over x minus I come out to 1 over x plus I times x minus I. And that's a good observation, Ty. We could actually, if we allow for the fact that I squared is -1, so x squared plus 1 is x squared minus I squared, we can actually use difference of squares formulas. X plus I times x minus I. So if we multiply both sides by x plus I times x minus I, we're going to get 1 has to be equal to a times x minus I plus b times the expression x plus I. And what can we do if we want to solve this equation for a and or b? I'm going to make a note over here that this is the standard 5 approach to how we would evaluate something like this. This is going to be the standard 4 approach, the partial fraction approach. Reagan, any ideas?
You could set x equal to I.
Yeah. We could say, don't let the I scare you too badly. I is just a constant number here. Imaginary constant number, but that's besides the point. We could solve that in the same way that we would if this was, say, x minus 2 and x plus 3. We could plug in numbers for x that'll allow us to simplify. Sorry, Regan, I've already forgotten. What did you propose we plug in for x?
I.
Okay, so if we plug in x equals I, let's see, on the left-hand side we'll still get 1. On the right-hand side we'll get a times I minus I. Well, I minus I is just 0. Plus b times I plus I, which is 2I. And, question I'll ask you again. If we look at this equation, how can we solve for one of our two a or b constants?
You just divide by 2I.
And what will that give us? Yeah, it's going to give us that b has to be equal to 1 over 2I. Which we could multiply by I over I if you want and get the I in the numerator instead of the denominator. And that would simplify to, what? Negative I over 2? Neato Dorito. So, Sarah, how can we do something similar to solve for A instead of for B?
You can plug in negative I.
Plug in negative I for x? Let's try that. If we plug in x equals negative I, we'll get 1 is equal to a times negative I minus I is negative 2I, plus b times negative I plus I is 0. And that'll give us a is equal to negative 1 over 2I. Which again, if we wanted to, we could multiply numerator and denominator by I to give us negative I over negative 2, which is the same as just I over 2. So A comes out to I over 2, B comes out to negative I over 2. And so then, if we want, we can go back to our original integral, plug in those values into a partial fraction decomposition. And what we'll get is integral from 0 to infinity of a over x plus I, so that's going to be I over 2 times 1 over x plus I, plus b, so minus I over 2 times 1 over x minus I. And we can set it up like this. So all of this is just like what we did in standard 4. The only kind of new thing here, I would say, is the fact that we have I as an imaginary constant being plugged in. But treating I as just being a constant, you can still set it up and evaluate it in the same sort of way. I'll go ahead and toss in a limit out here, I suppose. So here's a question. How do we integrate 1 over x plus I? We can pull the I over 2 out in front of the integral as a constant multiple if we want. But how can we find a function whose derivative is 1 over the quantity x plus I? James?
Well, I think a u sub would work now because the x is only 1 degree higher than the top one.
Okay, so what would you try for u?
X plus I.
Okay, so we could try u equals x plus I, which would make du equal to dx. Here we're treating I again as a constant. And I'm doing all sorts of things we haven't talked about, like how do you take the derivative of an imaginary function? But assuming it works this, but doing some hand waving and assuming it works the same way for imaginary functions as it does for real functions, as far as constants are concerned. If we did a u sub on this, we could actually integrate to get natural log of x plus I. And similarly, we could integrate 1 over x minus I to get natural log of x minus I. Evaluated from 0 to r. Dr. Gerstle, don't we need natural log of absolute value of stuff instead of just natural log of stuff? For this problem only, no. The reason being, if you're doing natural log and involving imaginary numbers, then it actually just becomes natural log of, the integral of 1 over x just becomes natural log of x instead of natural log of absolute value of x. But that's for this problem only. And it's because of the fact, and it's due to some technical reasons I don't want to get into great detail over, involving the fact that we're working with imaginary numbers. All right, so I'm going to do a little bit of sneaky factoring here. I'm going to write this as limit as r goes to infinity of I over 2 times the expression natural log of x plus I minus natural log of x minus I, evaluated from 0 to r. And here, I'm going to use a property of logarithms that you all may have seen before, which is that natural log of A plus natural log of B is the same as natural log of A times B. Or, similarly, natural log of A minus natural log of B is the same as natural log of A over B. And what I'm going to do is I'm going to rewrite this expression as natural log of x plus I over x minus I. So here I'm just kind of applying that second logarithm property that says if you have log of one number minus log of another number, you could take log of first number divided by second number. Okay, let's try evaluating our limit now. We're going to get I over 2 times limit as r goes to infinity of natural log of r plus I divided by r minus I minus I over 2 times natural log of 0 plus I over 0 minus I. Question. As r goes to infinity, what's going to happen to r plus I over r minus I? If we treat the i's as, again, just being a constant. What real number is r plus I divided by r minus I going to approach as r gets really, really, really big? Meaning the plus I and the minus I terms in the numerator and denominator are going to matter less and less. James?
Is it just 1?
Yeah. This expression is going to go to 1 as r goes to infinity, because the plus I and the minus I will become less and less important as r gets really, really big. That's just going to go to 1. So what this is going to give us is it's going to be I over 2 times natural log of 1 minus natural log of I over negative I. Natural log of 1 is 0, so this term just goes bye-bye. What's I divided by negative I? If we tried to take I and divide by negative I, how would things cancel out? Give someone else a chance. Okay?
Would it just be -1?
Yeah, the i's would cancel out and we'd just be left with 1 over negative 1, which is the same as negative 1. So we get negative I over 2 natural log of negative 1. Holy Toledo. Dr. Gerstl, you can't take natural log of negative 1. You can't take natural log of positive numbers. You can take natural log of negative numbers if you allow for i's to be involved. Dr. Gerstl, what does this have to do with I to the power of I? I was promised you would tell us what I to the power of I is. All right, let's do it. So we evaluated the same integral using 2 different methods. What I think we can do then is we can set this to say, hey, these 2 expressions should be equal to each other, since it was evaluating the same integral but in 2 separate ways. So if we set our answers equal, that's going to give us that negative I over 2 natural log of negative 1 is equal to pi over 2. Okay? Well, I'm going to multiply both sides by negative 1 here to get I over 2 times natural log of negative 1 is going to be negative pi over 2. And now what I'm going to do is I'm going to take e to the power of both sides. Get e to the power of I over 2, natural log of negative 1, is equal to e to the negative pi over 2. So what can we say about e to the I over 2 natural log of negative 1? Well, we can use another log property which says that r times natural log of a is equal to natural log of a to the r power. We can pull multiples out in front into powers inside of logarithms to say that that's going to be the same as e to the power of natural log of negative 1 to the power of I over 2. Pull this I over 2, in other words, into an exponent on our negative 1. Well, that's the same as, what happens when we take e to the power of natural log of something? Mary? Yes?
E and the natural log will cancel each other out.
Yeah, e to the natural log of x is just x. So in this case, e to the natural log of negative 1 to the I over 2 is just negative 1 to the I over 2. Okay, what can we say about negative 1 to the I over 2? Well, we said earlier that I squared is negative 1. So negative 1 should just be I squared. So we get I squared to the power of I over 2, which, using our exponent rules, is the same as I to the power of 2 times I over 2, and in the end, swoosh, swoosh, I to the I power. So when all is said and done, I to the power of I is going to be equal to e to the power of negative pi over 2. And what's mind-blowing about that is taking an imaginary number I to the power of an imaginary number like I. That's a real number. It's about, I don't know, 0.208. And that's how you can find I to the power of I using some integration madness. Alright, have a good one, everybody. Just so you all know, I'm not going to be testing you over any of this I to the I stuff. I just thought that this was kind of an interesting diversion. Sort of like a, here's how we can use some of the stuff we've been doing so far to prove a kind of cool mathematical formula, if you ask me. Hope you all have a good one. On Wednesday, we will pick things back up with the discussion of type 2 improper integrals.
Thank you.
I'll be around. Cool. See you in a bit.
Thank you, Dr.
See you later.